Hello everyone, my name is Hessah Alkhaldi and today I will be talking about shape-shifting alloys, specifically nitinol. This is the table of contents in which I will go over an introduction, the characteristics and properties, the applications, a 3D model structure, conclusion, and references. Now, to understand what is nitinol, it is a shape memory alloy made of nearly equal parts of nickel and titanium with approximately 45% nickel and 55% titanium. Now, this was first discovered in 1959 at the U.S. Naval Ordnance Lab by William, giving it the name nitinol, Ni for nickel, Ti for titanium, and Nol for the Naval Ordnance Lab, as they discovered that nitinol has solid-state phase transformations between martensite and austenite, and they discovered that it has widely used applications in aerospace, robotics, and biomedical fields. Now, the most unique properties nitinol has is its shape memory effect and superelasticity. Our focus is on how nitinol changes phases and how these changes are analyzed using differential scanning calorimetry. Now, to understand what makes nitinol unique is the shape memory effect, meaning nitinol remembers its original shape, reverting back to it when heated due to temperature-driven phase changes for martensite back to austenite. Applications leveraging this include actuators, stents, and even eyeglass frames. Then there is superelasticity, meaning it can stretch or deform significantly and up to between 10 to 30 times more than regular metals, instantly returning to its original shape upon unloading. And as this property is invaluable in stress-induced phase transformations from austenite to martensite and back, nitinol also stands out for its biocompatibility and corrosion resistance, making it ideal for biomedical implants such as stents, orthodontics, and surgical tools. It can safely reside in bodily environments long-term without corrosion, as well as the electrical and optical properties of nitinol. Since the resistivity varies between phases, the difference helps in detecting the phase transitions. Additionally, changes in reflectivity correlate with the material's phase state. Now, mechanically speaking, nitinol demonstrates high strength and elasticity and excellent fatigue resistance under cyclic loads, as austenite is stiff and strong while martensite is softer and more flexible. This contrast helps engineers choose the right phase for specific applications. Now, in the thermal properties of nitinol, these include distinct phase transitions occurring between approximately 70 to 40 degrees Celsius for martensite and around 50 to 80 degrees Celsius for austenite. These transitions involve latent heat, which is essential for the shape memory effect and superelasticity. The tool used to measure the flow of heat during temperature changes is differential scanning calorimetry, or DSC, as it identifies critical transition temperatures, latent heat involved in phase changes, the presence of intermediate R phases, and the overall phase purity. This guides material design, quality control, and performance optimization. Now, why does this matter? Understanding these characteristics helps us tune nitinol for precise applications, ensuring that they are reliable and their performance in implants and actuators are actually accurate. There are many applications of nitinol, but to narrow it down, we will talk about the biomedical devices, aerospace and automotive, robotics, and the consumer products. In biomedical devices, it is used for self-expanding stents, orthodontic wires providing constant pressure, surgical staples, and flexible dental files. Regarding the aerospace and automotive industry, they utilize nitinol in adaptive couplings, morphing structures for deployable antennas, and vibration dampers. Whereas in robotics and actuators, they are used for artificial muscles since the wires contract with heat, grippers or microactuators, they silent motion via thermal signals, and smart actuators which are reliable response in compact systems. Lastly, they are used also in consumer products such as eyeglass frames, since they have the ability to bend without breaking and return to their original shape. They are also used in electronic wires, making them flexible and more durable. The key benefit across all fields is that nitinol responds predictably to heat or stress, allowing safe, compact, and reversible motion in complex systems. To visualize the different phases of nitinol, we have the 3D model, where it starts off as a martensite phase and upon heating transforms into the austenite phase. Once the heat is cooled off, it returns back to the martensite phase. Now, to wrap up our presentation, we now know that nitinol's uniqueness lies in its shape memory effect and superelasticity, both enabled by a reversible solid-state phase transformation. These transformations between austenite and martensite allow nitinol to deform and return to its original shape under heat or stress. Its biocompatibility, fatigue resistance, and thermal responsiveness make it invaluable in fields like biomedicine, aerospace, robotics, and consumer products. As well as DSC is a powerful tool for analyzing nitinol's behavior, since it can accurately identify transformation temperatures, detect latent heat, R phases, and the thermal history, as well as it helps in material design, quality control, and performance tuning. Lastly, we were able to understand and characterize phase behavior through DSC, as it is essential to fully leverage nitinol's potential in real-world applications. These are the references used throughout the presentation. Thank you.